Welcome to Get EDUCARE. In this video, the efficiency of transformer will be explained. This class is one of the most important portion in exam point of view. Maximum times the numerical based on the efficiency comes to your exams like GATE, IAS and other PSU exams. So I'll request all of you to go through the video fully. Now the efficiency is defined as output by input into 100%. Therefore, it is given by output. Now, input is the output plus losses into 100%. Here, in this case, the output current is I2. This is I2. And the secondary voltage of transformer is V2 and a load of power factor cos theta 2. Therefore, output of transformer is given by E2 I2 into cos of theta 2. And the losses are generally, there are two types of losses. One is the copper loss plus another is the iron loss. The copper loss is given by I square R loss. The current through the load or the secondary winding is I2, that means I2 square, and what is the resistance of the transformer? That is equal to R02, where R02 equal to the resistance of transformer with respect to secondary. And what is the iron loss? Total iron loss is given by W of I. Therefore, total losses of transformer is I2 square R02, that is equal to copper loss plus iron loss W of I, that is your iron loss. Therefore, from this equation number 1, efficiency is given by output, this is the transformer output, E2 I2 cos of theta 2 divided by, again output is E2 I2 cos of theta 2 plus of total losses. Total losses is this is the total losses I2 square R02 plus of W of I. This efficiency is of transformer is at full load efficiency when the I2 is the full load current I of FL. Now, all of you know that copper loss at X of full load equal to the X square into full load copper loss. This formula we have derived in copper loss class. Please go through that video. Link will be given into the description box. Copper loss at X of full load is given by X square into copper loss at full load. That full load copper loss, this term is equal to, this is full load copper loss, that is equal to X square into I2 square R 02. Therefore, we can write down the efficiency at x of full load is given by, from this equation, okay, when efficiency at full load is this equation E2 I2 cos theta 2 divided by E2 I2 cos theta 2 plus full load copper loss plus of iron loss is given by x into E2 I2 cos of theta 2 divided by x into E2 I2 cos of theta 2 plus x square into I2 square R02 plus of iron loss. Now, suppose this is the equation number 2. Therefore, efficiency at x of full load equal to the x. This is the E2 into I2 is the VA rating of the transformer into cos theta 2 is the power factor divided by x into VA into power factor x into VA into power factor plus x square into full load copper loss plus of iron loss. We have to remember this formula. Now we have to find out condition for maximum efficiency. From equation number 2, in this equation, there are two variables. Number one variable is the load current I2, that is equal to load current I2, and another variable is the load power factor cos of theta 2. First, case 1. In case 1, we will differentiate the equation number 2 with respect to load current I2 considering load power factor cos theta 2 equal to constant. That means differentiate equation number 2 with respect to load current I2 considering load power factor cos of theta 2 equal to constant. Therefore, if I do the differentiate, then we will get the relation x square into I2 square R02 equal to W of I. Here, this is your copper loss, that is your iron loss. We can say when copper loss is equal to the iron loss, then the maximum efficiency will be occurred. Again, from here I can write down x equal to W of I into I2 square R02 of root from this relation. Therefore, x equal to root over of iron loss divided by full load copper loss. I2 square R02 is the full load copper loss, Wi is the iron loss. This condition will be satisfied for maximum efficiency. Again, one of the most important relation, where x equal to the percentage of loading. That means for maximum efficiency, the percentage of loading x is given by root over of iron loss divided by full load copper loss. The total loss at maximum efficiency is given by copper loss. This is the copper loss, x square I2 square R02 plus of iron loss. Here this copper loss equal to Wi iron loss, therefore iron loss plus of iron loss, that is equal to 2 into iron loss, is given by total loss at maximum efficiency equal to 2 into Wi, that means equal to iron loss. This is again one of the important relation for finding out iron loss at maximum efficiency. We have derived one relation, x square into I2 square R02 equal to Wi. That means copper loss equal to iron loss for maximum efficiency. Therefore, we can write down again for maximum efficiency, I x square into I2 square into R02, this equation equal to W of I iron loss. Here x into I2 square equal to W of I divided by R02. This current I can write down I2 dash. That means secondary current at maximum efficiency is given by root over of W of I iron loss divided by R02. Therefore, I2 dash equal to, here W of I divided by I of FL full load current square into R02. This is within root of R, and this full load current I can write down outside like this. When this come outside, this full load current and full load current will be cancelled out, then this relation will be satisfied. If we multiply both sides by E2, that means I2 dash into E2 equal to I of full load into E2 divided by Wi divided by I of full load square R02. This is your kVA rating corresponding to maximum efficiency. Therefore, kVA at maximum efficiency equal to this is again full load current into voltage, kVA at full load, kVA at full load root over of W of I is the iron loss. This is your iron loss divided by this term, full load current square into R02 is your full load copper loss. This is again one of the important relation. You should remember this relation also. We have to draw efficiency versus load current I2 graph. This is your efficiency axis, this is your load curve axis, load current axis, efficiency and load current I2. When the load current increases, then efficiency also increases like this. At some point, at a particular value of load current, the efficiency becomes maximum. This is maximum efficiency. If we increase the current beyond this point, then the efficiency will decrease. This point is the maximum efficiency point. Just we have derived. So maximum efficiency iron loss equal to the copper loss. Here copper loss equal to the iron loss at this point. Suppose this is the point O, this is A and this point is B. Here in the OA portion, iron loss W of I is greater than copper loss. Here iron loss is greater than copper loss. That means W of I is greater than I2 square into R02. And if we, in this region, if we increase the load current, I2 is increased, then the efficiency of transformer also increases. At point A, here in this point, here copper loss equal to the iron loss, but W of I, iron loss equal to copper loss. Here. That means here efficiency is maximum. In the AB portion, here the iron loss is less than copper loss. That means in AB portion copper loss is greater than iron loss. Copper loss is the I2 square R02 is greater than iron loss W of I. In this portion, if I increase the load current I2 in this direction, then efficiency decreases. Now, if I draw a parallel line of x-axis, then we have see this is your I2 dash, suppose this is your I2 double dash, and this is the efficiency. The efficiency, it can be obtained at I2 dash as well as I2 double dash, here and here. That means efficiency graph is called double valued graph, since the same efficiency can be obtained at two different current. One relation, efficiency at x of full load is the x into E2 I2 cos of theta 2 divided by x into E2 I2 cos of theta 2 plus x square into full load copper loss, that I2 square into R02 plus of iron loss W of I. This is the equation number 2 as we have derived earlier. Here another variable is the load power factor cos theta 2. If we differentiate this equation with respect to cos of theta 2, load power factor angle, considering load current I2 equal to constant, then we will get cos of theta 2 equal to 1. That means at unity power factor or resistive load, the efficiency is maximum. If I draw the efficiency versus power factor, then if the power factor increases, efficiency also increases like this. This is 0.4, this is 0.6, and like this is 1, and here this is the maximum efficiency. Now we will practice a questions of GATE 2004. A 500 kVA 3-phase transformer has iron loss of 300 watt and full load copper loss of 600 watt. The percentage load at which the transformer is expected to have maximum efficiency, and you have to find out the percentage of load X. Here iron loss W of I is equal to 300 watt and the full load copper loss is given by 600 watt. At maximum efficiency, all of you know percentage of loading X is given by root over of iron loss divided by full load copper loss. This relation we have derived in the theory portion in this video. We must have to remember this relation, that will be given by root over of, here iron loss is given by 300 watt and full load copper loss is given by 600 watt. That is equal to 1 by 2 root over, that is equal to 0.707 equal to 70.7% is the answer. Option B is the correct option. Practice another numericals. GATE 2003. A single phase transformer has a maximum efficiency of 90% at full load and unity power factor. That means maximum efficiency is 90%, then the power factor will be the unity 1. Efficiency at half load at the same power factor, that means unity factor, is 4 options. Here we have derived one relations of efficiency at X of full load is given by X into VA into power factor divided by X into VA into power factor plus X square into full load copper loss plus of iron loss. This is the one of the important relation we must have to remember always. Here X is the percentage of loading. Here at maximum efficiency, here maximum efficiency will open at full load. That means for maximum efficiency, X equal to efficiency equal to 90%, that is equal to 0.9 For a maximum efficiency of 90%, the value of x equal to full load, that is 1. And what is the power factor? Cos of theta 2 is also 1. Therefore, from this relation I can write down this is equal to maximum efficiency 0.9 equal to x, value of x equal to 1 into VA, volt ampere, into power factor. Power factor is again 1 divided by 1 into VA into power factor 1 plus x square, that means 1 that is square. Now here again we have derived one relation for maximum efficiency in this condition, that full load copper loss equal to the iron loss. In the previous theory we have derived this. Therefore, in the full load copper loss, this can be replaced by iron loss plus of this iron loss W of I. From this relation I can write down iron loss equal to 0.0555 into VA. This is iron loss. Therefore, full load copper loss will be the same. Full load copper loss is also given by 0.0555 VA. Then we have to find out the efficiency at half load, half of full load. That means here x, value of x equal to 1. Sorry, value of x equal to half. If I use this formula, value of x equal to half into VA into power factor. Here the same power factor. That means here cos theta 2 equal to again 1. If I put the power factor equal to 1 here, divided by x equal to half into VA into 1 plus of x square equal to half, the square. Full load copper loss is given by this, that means 0.0555 VA plus of iron loss. Iron loss is again this relation 0.0555 VA into 100%. Then the efficiency VA will be cancelled out. If I do the simplification, I get the efficiency at half load is given by 87.8%. That is option D is the correct option. Thank you for watching these videos.